Chemical Bonding, Chapter 8. Let's do a quick review of different kinds of chemical bonds. We have ionic, electrostatic attraction between ions, such as magnesium oxide, potassium dichromate, nickel oxide, all with metals and nonmetals. Covalent bonds, sharing electrons between non-metal atoms typically. And metallic bonds, which hold metals together and alloys together, and they're sharing delocalized electrons between a whole lattice of atoms. First, ionic bonding. Okay, we looked at some trends in the last chapter that had to do with electrons being added or taken away. So, for instance, we saw that it takes 459 kilojoules to remove electrons from sodium. So you have to input that much energy. It's called the ionization energy. And chlorine, when it gains an electron, as in ionic bonding, it releases 349 kilojoules per mole. That is called, electron affinity. Let's do a quick review. Now, if you think about those together, that's a net absorption of energy. Electrostatic attraction between ions. Why do you have this super, such as magnesium oxide, potassium dichromate, nickel oxide, all with metals and non-metals, not being accounted for? Covalent bonds is sharing electrons between the ions once the ions are made. Typically. And metallic bonds release a lot of energy when they come together and alloys together, more stable for them, and they're connected with delocalized electrons between a whole lattice of atoms. So this is called lattice energy, ionic bonding. And as it's measured, it's the energy required. We looked at some trends in the last chapter that had to do with electrons being added or taken away. Ions. So, for instance, this is the opposite of what I just talked about, but it's the same amount of energy just measured in an opposite way. Input that much energy. So the energy we're talking about, the ionization coming together, is the same amount of energy with when it gains an electron, as the lattice energy as in ionic bonding. It releases 349 dictated by Coulomb's law, which we saw recently when we were talking about the PES, electron affinity, in which we've got two charges multiplied together divided by the absorption of energy. So why do you have this super exothermic reaction when sodium chloride is made? Energy then increases with the charge on the ions not being accounted for. So if you look in this chart, is lithium, the attraction, all of these are between the ions once the ions are made. They release a lot of energy when they come together because it's over so here much more stable for them to be connected with an ion and even a plus they're attracted to. -3 ions. So this is called lattice energy. You can see the trend, and as its charge goes up, it's the energy required to completely separate a mole of solid ionic compound into its gaseous higher charge, more energy to separate. This is the opposite of what I just talked about, but it's the same the size of the ion just also measured in an opposite lattice energy. Let's see if we can see the energy we're talking about, the ions coming together, is the ions that are the same cation with different anions. Energy needed to take them fluorine, chlorine, iodine are all dictated by Coulomb's law. Fluorine we saw recently when we were talking about the PES, and then chlorine, and then two charges multiplied together divided by the distance between those charges. The atoms get bigger, the ions, get bigger. The lattice energy goes down. Energy then increases with the charge on the ions are farther apart. So if you look in this chart, lithium, fluorine, all of these are less energy needed. Minus less energy of attraction between them. Over here we've got plus 2, minus 2 ions. The complete process of going from the elements of sodium and chlorine. I'm sure you can see the trend as the charge goes up. The net change amount is a release of energy, as we know, it's an exothermic reaction. Energy goes up. So here's all the steps that are combined into what's called the Born-Haber cycle. It also the size of the ion also impacts the lattice energy. Takes some energy. Let's see if we can see the trend. Then the chlorine, let's in this case look at separated. ions that are the same cation with different anions. So then fluorine, the sodium atom, chlorine, iodine are all attached here to a lithium. And an electron is removed. That's called the ionization energy. And then that was chlorine and then iodine in terms of size. Here, so as the chlorine takes on that electron, and it releases, the lattice energy goes down. Some kilojoules of energy ions are farther apart. So the net change right now is still there'll be less energy needed, but there's less energy of attraction between them. That attraction between the ions. So it's the opposite of the lattice energy. Is the energy released? The complete process of going from the elements of sodium and chlorine all the way to sodium chloride. Quick review of electron configurations of ions. Sodium release of energy, as we know, it's an exothermic reaction, to a noble gas all the state steps to be stable. Chlorine into what's called from a halogen to a -1 ion to be stable. First, the sodium together released all that energy, vaporized, takes some energy. Okay, now in covalent bonding, then rather than sharing, transmitting electrons and then being attracted, they are sharing electrons. That takes energy. And there's attractions and repulsions involved in those bonds. Then the sodium atom is ionized. So there's attractions between the electrons and the nuclei. That's called the ionization energy. There's repulsions that was at 495 between the electrons and repulsions between the nuclei. Here, those all have to be balanced out. Takes on that electron, when they do so, it releases. They get closer and closer together, and at kilojoules, the lowest energy possible distance for the bond is the lowest energy. So the net change right now is still the positive and the attraction. But here's where we get that attraction between the ions. We can depict these with simple Lewis structures, which we will be the lattice energy class is the energy released. These are all single bonded simple molecules with the goal of having everything have an octet. And quick review of electron configurations of ions. Single bonds, then sodium went from multiple bonds. An S1. So a single bond just indicates that there's one shared pair. Went from a halogen to a -1 ion to be stable bond, and came together shared pairs and released all that energy. Here's some Lewis structures. Okay, now in covalent bonding, nitrogen. Rather than sharing those multiple bonds, transmitting electrons and then being attracted, they are sharing electrons. And there's attractions and repulsions involved in those attractions. So when you have multiple bonds, attractions between the electrons and the nuclei, bond distance decreases. There's repulsions between the electrons and repulsions between the nuclei. Because those all have to be balanced different kinds of elements, and when they do so, be shared unevenly. They get closer and closer together, and how they're the shared. Lowest it can be pure possible distance for the bond equally is the lowest energy that minimizes the repulsions and the diatomic elements labeled. We can depict these with simple Lewis structures, which we will be practicing in class. These are all single bonded simple molecules with the goal of having everything have an octet if you prefer. And then not everything can get an octet with one atom bonds, then you have to do some multiple bonds. Has a greater attraction for bonding electrons. So a single bond just indicates that there's one shared pair, and the red end of the molecule two shared pairs in a double bond, and three shared pairs in a triple bond. Here's some Lewis structures. Hydrogen, oxygen, nitrogen. If there's a large enough difference, of course, you get multiple bonds impact the bond and then they make an ionic bond. Just as the attractions and repulsions did. You've got electronegativity drives. So when you have multiple bonds, what kind of bond is produced? And even though it is a continuum, there's a covalent bonds. There's some values that can help you have an idea. Two different kinds of elements can often be shared unevenly. A difference in electronegativity to how they're shared. As I like to call it, it can be pure covalent of shared equally greater than 1.7, and that tends to be metals, the diatomic and non-metals. Then you typically have an ionic bond, known as if your difference is greater than 0.4 and less than 1.7, then you typically got a covalent bond, or polar covalent. And then there's polar covalent, where one atom has a greater attraction for bonding less than 0.4. They're often considered with different colors, and the red end of the molecule is usually very important. Electron heavy, and the blue end is electron deficient. If there's a large enough difference, of course, you get ionic polarity. You have something called a bond dipole that can be measured with a dipole moment. It's not something we're going to calculate, but drives, just FYI, you take the charge what kind of bond distance between the ions produced, and that gives you something measured in even though it is a continuum, a moment. There's the bigger the dipole moment, there's some values that can help you have an idea of what kind of bond you've got. Difference between if you've got a difference in electronegativity, E-neg, and you can see here as you greater than hydrogen bonding with very electronegative that tends to be metals all the way to iodine in the halogen column. You typically have an ionic polar bond. Iodine's really large. If your difference is so the bond length is large and that reduces the dipole moment, then you've typically got a covalent quick review bond, of naming polar ionic compounds. You start with the metal, end with a non-metal, and if it's less than 0.4, IDE at the end. It's often considered always at IDE unless not enough polyatomic to be it's an 8 or an 8. But if it's just two elements, it ends in IDE. You add Roman numerals. All right. So when you get has more than one polarity, you have something called a bond dipole that can be measured. Whereas in molecules, you don't have any Roman numerals. We're going to calculate, but just the ratio of atoms attached times the distance between the such ions, as in oxygen di, something measured in Debbie. There's two fluorines attached to the oxygen. The bigger the dipole moment, the greater the oxide. Hydrogen sulfide should probably be written as dihydrogen monosulfide, but historically it's always been hydrogen sulfide. And you can see here as you it's not written that way. Go from hydrogen bonding with very electronegative fluorine all the way to iodine in the halogen column. Find the sum of all the valence electrons. Polar bond. Iodine's really large. If it's an anion, so the bond length is large, such as that reduces the dipole moment. Sulfate. 2 minus. Okay, quick review of naming ionic compounds. You start with the metal, end with the non-metal, and then you would add 2 electrons to the total. If it's a positive cation, it's a polyatomic, NH4 plus, you subtract an electron. But if it's just two elements, it ends in IDE. So let's look at this. You add Roman numerals. Nitrogen has 5 valence electrons. One possible hydrogen charge. Has 1 we'll each. Practice that in class. There's 4 of them. Whereas in molecules, you don't have any Roman numerals, and to indicate the ratio of atoms and attached, you use prefixes in that such as in oxygen difluoride. That's how you count di, meaning there's 2 fluorines attached to the oxygen. Then you put the central atom as the least electronegative element that isn't hydrogen. Sulfide should probably be written as dihydrogen monosulfide and connect the outer atoms to the central atom. It's not written because they're going to be bonded, and each of those dashes represent a pair of electrons. Quick review on writing Lewis structures. Fill the octets of the outer sum of all the valence electrons and see if you've used up all the electrons. If it's an anion, in this case, such as we started with the need for 26. Sulfate, we used 6 to bond the phosphorus to the chlorines. Let's try that again. That left us with 20. We added 18 around the chlorines to give them octets. Then you would add 2 electrons to the total. If so we want to look to see if any other atoms need NH4 electrons to make an octet. Subtract an electron. Looks like the phosphorus does. So if we add the octet to phosphorus, nitrogen has 5 valence electrons. We have a complete. Hydrogen has 1 each. Lewis structure, and there's 4 of them. Used up all the electrons, and everything has an octet. But you have to subtract 1. Okay, if you run out of electrons before everything gets an octet, then you have to double or triple bond. So that's how you count. So you take some of the electrons that were unbonded, then you put the central atom between as the least electronegative element that isn't hydrogen. The one hydrogen can only bond once. And in this case, hydrogen cyanide, it's going to be a triple bond the outer atoms the carbon to the central atom. And now, because they're going to be bonded, and each of those dashes represent a pair of electrons. And nitrogen has 2, 4, 6, 8. Fill the octets of the outer atoms. This is a Lewis structure we would draw see if you've used up all the electrons yet. In this case, we started with the need for 26. Look at an actual, we used 6 structure of ozone that's measured with X-ray crystallography. That left us with 20. We find that rather we added 18 around the chlorines to give them octets. The single, so we have 2 left over on one side and a double on the other side. Any other atoms need more electrons to make an octet. Looks like the phosphorus does. So if we add the octet to phosphorus, then that would indicate they have different bond lengths. You have equal bond lengths. We've used up all the electrons and everything has an octet. Okay, if you run out of electrons before everything gets an octet, then you have to double or triple bond. So that leads us to believe that you take some of the electrons that were unbonded, in which one Lewis structure can't adequately depict the molecule that had them with the one who needs them. Something in between. And in this case, hydrogen the double bond resonating back and forth, bond between and in reality, and the nitrogen. It's shared amongst all hydrogen has its 2, carbon has 2, 4, 6, 8. That's what's going on when nitrogen has 2, 4, 6, 8. Multiple possible Lewis structures that add up. This is a Lewis structure we would draw for ozone. You use multiple structures, resonance structures, to describe the molecule. Look at an actual structure of ozone that's measured with resonance is just like mixing paints. We find blue and yellow make green. 2 different resonance structures, single can be blended on one together side and a double on the other side bonds. Okay. In truth, the electrons that form that would indicate they'd have different bond lengths. The second carbon-oxygen bond and the double bonds don't always sit between carbon and oxygen, but can move among the 2 oxygens and the carbon. So as I said, they kind distribution of stay in between amongst all the atoms. They don't. So that leads us to believe that this is a resonance structure in which one Lewis structure can't adequately depict the molecule. I wanted to mention that in the outline, something in between. I just remembered that there's a section the double bond resonating back and forth. And in reality, no longer included in the AP test. So I eliminated that, but I forgot to take it off the chart. That's what's going on when you see, don't worry about that, multiple possible Lewis structures that add up to be the same thing. Okay, so back to resonance. These electrons that are resonance structures are not localized, but they're more like a metallic bond where they're delocalized. It's not easy to draw them together. So resonance is just like mixing benzene is a really good example of a resonance structure. So they have alternating resonance single and double bonds can be blended together to give you what is the reality. Turns out all the bond lengths are equal, and so rather than drawing 2 different structures all the time, this is what you normally see for a benzene ring because it shows the second carbon-oxygen bond and the double bonds don't always sit between carbon and oxygen, but can move. Okay, among a couple exceptions to the octet and the carbon. So as I said, they 3 types of ions or molecules that don't follow. Set of atoms. They don't. You might have ions or molecules with an odd number of electrons. You might have some with less than an octet and some with more than an octet. Okay, I wanted to mention that on the outline, I just remembered relatively that rarely you can get an odd electron. Is no longer included in the AP test. Very unstable and very reactive, so they don't last very long, but they do exist. Notes outline. So nitrogen oxide, not responsible nitrogen monoxide, for example, is one. And okay, so back to resonance structure. These electrons that are resonance electrons, the nitrogen are not in this case localized, but they're more like a metallic bond where they're delocalized. Fewer than 8 electrons. Benzene is a really good example of a resonance structure. Of course, hydrogen, which they have alternating, but also in the case of boron, between 6 carbons boron, in a ring. When it makes structures, turns out all the bond lengths are equal. Double bond to give itself rather than drawing 2 different structures all the time. This is it only has 3 valence electrons for a benzene ring. So, and being a very small atom, we find the double bond is distributed. It gives it a negative charge, which it can't handle. Anyway, there's a couple exceptions to the octet rule. And boron tends to be 3 types of ions or molecules that don't follow. 6 valence electrons. You might have ions or molecules with an odd number of electrons. Are examples where you might have some with less than an octet and some with more than an octet. Be a fairly stable. Let's look at a couple examples. Relatively rarely, filling you can get the central atom results in a negative charge on the central atom. They're very unstable and very reactive, so they don't last very long, but they do exist. Octet of the central atom. Nitrogen oxide. Well, that has to do with formal nitrogen monoxide, for example. It really only happens with boron. It's a resonance structure between these 2 options. Notice how the nitrogen more than 8 electrons has 7, and the oxygen in this case. Some elements, such as phosphorus and arsenic and sulfur, fewer than 8 electrons. With more than 8 electrons. That happens with Of course, hydrogen, it's allowed to expand, but also in the case of on the third period of the periodic table or structures. Presumably, that's because there's d orbitals available for those extra bonds to use. Although right now there's a big controversy. It only has 3 valence electrons actually involved, and being a very small atom, we find it does follow. It gives it a negative charge, which only atoms from the third energy level and higher can have. And boron tends to be happy with 6 valence electrons rather than 8. All right, so hydrogen, more formal charge stuff are examples where you can get structures with fewer than 8 electrons and be a fairly stable molecule. Let's skip this. All right, the lesson is covalent bond the octet of the central atom results in a negative charge on the central atom by determining how much energy is required to break the outer atom. Don't fill this called bond enthalpy, and we have looked at this in thermodynamics, so this should also be a bit of a review. It really only happens with boron. For chlorine to chlorine is 242 kilojoules per mole. Okay, more than 8 electrons. Lots of other bond enthalpies, and some elements, depending on the type of atom and the number of bonds, and sulfur, multiple bonds, as you can see, have higher bond enthalpies than single bonds. It's allowed to expand. The octet of average bond enthalpies are positive because bond breaking is an endothermic process. Bond formation presumably that's because there's d orbitals available for those extra bonds to use. Although right now there's a big controversy. The average bond enthalpies are not actually involved in enthalpies. Sometimes they can change a little bit. Follow say carbon hydrogen is in methane versus in a bigger molecule level and higher can have what's recorded are average. And they can be really useful when you want to know the energetics of a reaction. You don't have to do. You can calculate how many electrons break and how many bonds form, and figure out the difference to find the delta H, just as we did in covalent bond strength. Thermodynamics unit. Most simply, the strength of a bond is measured by determining how much energy is required to break that bond. Energy. It's called bond products, and we have looked at this in thermodynamics, so this should also be a bit of a review. Minus bonds formed. For chlorine to chlorine is 242 kilojoules per mole. There's lots of other bond enthalpies, and it varies depending on the type of atom and the number of bonds. Add up the broken, and as you can see, subtract out higher bond enthalpies and single bonds. Add up the formed and subtract out the broken, and you get the overall average bond enthalpies are positive because bond breaking is an endothermic process. Bond formation is exothermic. Always deserves another repeat. We can also measure an average bond length. Note the average bond enthalpies are not absolute bond enthalpies. If you look at this, they can change a little bit. Single, double, triple, they get smaller. Carbon hydrogen is in methane versus in a bigger molecule, but single to double, triple, multiple bonds brings them in closer. And they can be really useful when you want to know the energetics of a reaction. You can calculate how many electrons break, and there we have it. How many Thank you for watching, and figure out the difference to find the delta H. And I will see you tomorrow in class. Have a great night. Thermodynamics unit. Hess's law. Energy from the products, and it's a lot like Hess's law. Bond enthalpies of bonds broken minus bonds formed give you the delta H of the reaction. There's one more example. So, add up the broken and subtract out, add up the formed and subtract out the broken, and you get the overall delta H. I'm confident you all are very comfortable with this. We can also measure an average bond length for the different bond types. If you look at this, you can see single, double, triple, they get smaller just as is expected. As you go from single to double to triple, multiple bonds brings them in closer.